Okay, so today I'm going to be showing you the work I did on my solar sense board for my solar car team. So to give you a bit of context or background, the way this sense board works is it basically communicates to MPPTs externally off the board and monitors the communication, the information they relay to a microcontroller all over SPI. So this could be information such as fault conditions or uh, internal voltage, um, etc. So the way the solar sense board works is you have solar cells here, and they go through MPPTs that change their internal impedance. Each of these MPPTs, five in series, and then each of those sets in parallel, go to ideal diodes, and then they charge up a battery. And the ideal diodes are basically a way to have zero voltage drop without having the battery discharge back into the solar cells. If you're unfamiliar with how an IV curve works, I have one pulled up here. So the way it works is when the MPPTs change their internal impedance, um, they're placed on a different part on this red curve. And where this red dot is where maximum power transfer occurs. And if we create a blue curve, which is voltage times the current, we see that maximum power occurs at this blue dot over here. So they're on the same x-axis region. Um, and the MPPTs do that, of course, all internally. Now that you have the context, let's go into the actual schematics on the board and what we did. So if you look at this controller board, sorry, let's start looking at the top sheet first. So the top sheet shows us is that each of the MPPTs are connected in series, and then we have a schematic for the current sense, a schematic for thermal management. So these are just thermistors that tell us how the temperature is behaving, and if the temperature is too low, they turn a fan on or off. And then we have a controller board that just monitors everything, which is our STM32 MCU. So if you go to the controller board interface, um, it just has the SPI lines that communicate to each MPPT. Things like turning off the fan and on and detecting its speed with fan sense. We have the chip select for each of the MPPTs, and we're detecting the current as well. With this goes through a low pass filter and then it goes to an ADC pin. And then we just have LEDs for the power. Moving on to the next schematic, current and relay sense. So this is low side current, so it takes the ground of the last MPPT goes to this Hall effect sensor, and then this Hall effect sensor outputs a voltage um, that goes to, as I was just showing you, our microcontroller, and then we detect what the voltage is um, with an ADC, and we can basically map out what the current is as well. Uh, the rest of the schematic, um, basically the way it works is we have a buck converter that steps down from 12 volts to 5 volts, and then we have two linear dropout regulators. Um, Sorry, we have isolators that go from 5 volts to 5 volts because we want to isolate the SPI communication between the MPPT and the microcontroller, just so we don't fry the microcontroller. So to do that, we have to isolate the power. And one of the ways to do that is to use 5 volts to 5 volts isolation. And then after that's done, um, we can just connect. So moving on to the MPPT interface. Um, this is why we need to isolate because um, we need to isolate the power rails on the SPI on the SPI isolators because this SPI isolators isolates the channels of the SPI, but it doesn't isolate the power. So we needed the that 12 volt to 5 volt buck converter, and then the 5 volt to the 5 volt isolator, and then we use the 5 volts to a 3 volt 3. There's a linear dropout regulator, and that way we get our isolated channels. One from this is the isolated channel, and this is just for the microcontroller. Next, we have thermal management, and these are just a bunch of thermistors uh, that monitor the temperature of the board. Of course, we have resistor dividers to scale down the voltages we sense from the thermistors. Sorry, the voltage drop we detect across the thermistors. And then we have these non-inverting amplifiers. So non-inverting amplifier, the way it works is 1 plus RF over RI gives you your gain. So here our gain is 26.5. And then we branch off these temperatures to the microcontroller and read them accordingly. And then here we're just detecting, we're using a PWM pin on our microcontroller to change the speed of the fan. And these passives are just suggestions given in the data sheet. And then the Zener diode just prevents injection current from going into the PWM pin. And if you look at the PCB, this I also wrote it all by myself. So I did all the schematics and wrote everything by myself. So it's almost done. It just needs review. And you'll realize that the power traces are thicker than the rest of them. And we're probably going to add like ground pores, sorry, power plane pores close to IC pins. So if we go to 3D view, this is how it looks in 3D view. This is our controller board or microcontroller. Um, and just for reference, I did not do this off scratch, but the whole point of this board was to update it from a previous board. And the previous board had many complicated things that we did not need that scaled up the cost a lot. So the goal of this board was to just scale down the cost. Like we had a decoder and a multiplexer for the SPI, and we didn't need it if we managed our pins in a smart way. And the way I looked about this is that we also had a 16-bit ADC, and this was taking up pins too. And we didn't need that because the current sense that we're using, its resolution doesn't match 16 bits. Okay, it's not accurate to the point where us using 16 bits would benefit. So we just used one on the STM32, so that saved us cost. The other thing is the MPT interface had a voltage sense, so this would detect voltage on the high side. But we didn't need to detect voltage on the high side because if the solar car failed in the middle of the competition, we just take a multimeter and check which MPPT was bad and just replace that one. Um, we also have found cheaper SPI isolators, so then that saved cost as well. Uh, the isolator too, like before, we just had a 3 volt 3 to 3 volt 3 isolator. But this was $8, which was very expensive, and we needed two boards and several boards as well, just in case we messed up. So this would ramp up cost way too high. We also had current relay sense. We realized that we had ideal diodes in the bay, like in our workstation, so we didn't need it. So we just took that off and just decided to connect it externally. We also had a power driver that was driving a relay so that we wouldn't waste too much power when we're detecting current, which is stupid and doesn't save us that much power anyway, and drives up cost way too high. And the goal of this project was just to drive down cost. And then over here, the thermal management schematic didn't really change, but that's about all. And we also reduced the area of the solar sensor board too, because the solar sensor board was bigger before because it had multiple components. So it's huge compared to the new one. So the new one accomplishes the same functionality with almost the same functionality with lower cost and lower size. So yeah, that's the solar sense board I revamped and designed. Um, Let me know if you have any questions, and thank you for watching.